Bismillahirrahmanirrahim. Hello students, this is Tashkil and today going to give a lecture on IGCSE Physics topic, that is radioactivity, and in the subtopic we have to discuss half-life today. While talking about its syllabus outline, half-life, we have to study the term half-life and how we can do the calculations for the radioactive substances using the tables of the decay curves, and in the supplement we have to use the data or decay curves from which background radiation has not been subtracted. So we will look upon background radiation concept as well. Well, talking about its importance in exam, 1 to 2 MCQ can come from this concept, and in extended response questions, 2 to 6 marks can come from this topic. Well, let's talk about half-life now. Half-life is represented with a symbol of small t and at subscript 1/2. So this is the symbol for half-life. So now we'll see that how we define it. Before I tell you the definition of half-life, let me tell you a very simple example. Let's say we are having some amount of radioactive element, and in it these are the atoms. You know that the radioactive substance is said to be unstable because all the atoms or the nuclei are having some amount of energy, excess energy in them, and they emit this energy in the form of some radiations, and the radiations can be alpha particle, it can be beta particles, or these can be gamma radiations. So three types of uh, radiations are emitted from these unstable nuclei, which are said to be radioactive. So what would happen to the nuclei when they are releasing these energy? Of course, the nuclei, when the nuclei are emitting their energy, they are becoming stable, right? So half-life is the time in which roughly half of the number of nuclei becomes stable. It means if you have 100 nuclei, if you have 100 nuclei and those nuclei are unstable, it means they are releasing energy. So we have to look for the time in which 50 of them got stable. Got stable means that they have emitted their energy in the form of alpha, beta, and gamma rays, and now they have no more energy. So the time taken by half of unstable nuclei to become stable is known as half-life time. So we can write the definition as time taken by half of unstable nuclei to become stable by emission of radiation is known as half-life time. Okay, now there are several ways to calculate the half-life. So next question is how to calculate half-life of a radioactive substance. Now, every radioactive substance is having a certain value of half-life that can be very longer. Let's say uranium-235 is having a half-life of nearly 16,000 years. It means if you have 10 nuclei, unstable nuclei of the uranium, so 5 of them, in order for 5 of them to become stable, 16,000 years will be consumed because its half-life is 16,000 years. And there are some radioactive elements or radioactive nuclei which are having very short half-lives as well, right? So let's say we talk about cobalt-60 and it's having a half-life of nearly 2 minutes. So it means if you are having 10 nuclei of cobalt, then in order for 5 nuclei to become stable, it takes nearly 2 minutes. So all the radioactive elements, the unstable elements have different values of half-life. Now the question comes how to calculate it. So calculation methods. So if you want to find half-life, there are several methods. The first of them is the tabular method. Okay, tabular method, of course, contains a set of data that is given to you, and you have to use that to find the half-life of a given radioactive element. For example, I'm going to draw a table, and then what you'll see is how to find the half-life. Okay, let's say the first is number of unstable nuclei. The second column is time, that is, let's say, in hours. We have some values given over there, and let's say these values are at time 0, number of unstable nuclei were 1000, and after a time of 1 hour, they become 700. After a time of 2, they become 500. After a time of 3, they become 350, and after a time of 4, they become 250. So now what is our task? We have to find the half-life of this radioactive element for which the data is given. So now we have to see that if we see initially at time of 0, 1000 nuclei were unstable. And after time of 2 hours, 500 remains unstable. It means 500 are stable now. So we can write 500 stable. So half of them stable, half of 1000, and the time they took is 2 hours. Similarly, we see that out of 500, 250 becomes stable and 250 remains unstable. So it means over here, 250 are stable now, like that is half of 500, and it took another 2 hours. So it means that it's both half-lives are 2 hours, 2 hours and 2 hours. It means the average half-life is 2 plus 2 over 2. So that is 4 over 2 and 2 hours. So the half-life of this radioactive element is 2 hours, which we have calculated through tabular method. Second method is decay curve graph. So we'll go on the next page. So for the decay curve graph, I'm going to draw a graph over here. The time is there, that can be in hours, and over here, activity rate can be given. Activity rate that will be in pounds per second. Okay, so initially, let's say a graph is given like this, and all the values are given along y-axis. So let's say this is 1000, this is 750, this is 500, and this is 250. And then over here, all the time values are also given. Okay, so we'll see that this is like 2 hours, 4 hours, 6 hours, 8 hours, 10 hours, 12, and 14 hours. So what is our task? We have to find half-life. So we'll now see that originally at time 0, 1000, what was the activity rate? 1000 pounds per second. So we have to look for half of it. So half of 1000 is 500. So at 500, the time value is 6 hours. It means the first half-life is 6 hours because the count rate decreases from 1000 to 500. Now we have to look for the second one, that is from 500 to half of it, which is 250. So when you look over here in the table, it is 10. So we'll see that from 6 to 10, 4 hours are there. So the second half-life is 4 hours. So when you have to find the average half-life, because the half-life is for the radioactive nuclei are not fixed, right? They can be different. It can be different, but the difference would be very slight. So when there is difference, so you will take at least two readings and you will take them, you will take their average. So you will say that the average half-life for this radioactive substance is 5 hours. Next, we have to look upon background radiation. Okay, so what is background radiation concept? Background radiations are actually the radiations present in the atmosphere due to sources which are not visible on which are not visible in the atmosphere. Let's say um, let's say this is sun. So some cosmic rays coming from sun or from outer space, and then some underground radioactive sources, underground radioactive sources, and then the radon gas coming from the Earth's crust and going into the atmosphere. Let's say this is the atmosphere, and then some hospitals, they have some radioactive elements to treat the cancer and the other things. So they have some radioactive substance. So they can also emit the radiation that can be penetrated into atmosphere, and some power plants, atomic power plants, using uranium as a fuel. So they can also, some radiation can also leak into the atmosphere. So all these things, like the cosmic rays, the hospitals, the power plants, the radon gas, the underground radioactive sources contributes towards the background radiation in the atmosphere. So the typical value for the background radiation is from 20 to 30 counts per minute, and measured through GMT. So background radiations are actually not harmful. So these are low or very low ionizing radiations present in atmosphere due to some sources. And I told you the sources that are cosmic rays, hospitals, power plants, atomic power plants, of course, radon gas, and other radioactive sources. So the typical value is 20 to 30. So what we have to do while finding the half-life? So we have to see its significance in calculations. So what we have to do is we have to subtract them. Subtract from count rate of a radioactive source in order to find half-life of that source. Why I've written that? Because look, let's say if this is the GM tube and this is the rate meter which gives you the reading. Let's say if nothing is there, right? So then although there is nothing, but GM tube is still giving reading of 20 counts per minute. So we will say that these are background radiations. These are background radiations because nothing is there in front of GM tube. So that might be due to cosmic rays or underground radioactive sources or things being used in the hospitals for the treatment. So these are the background radiations. Okay, this was the first step. In the second step, what we'll do is we'll put the same GM tube in front of, let's say, um, a material, a radioactive material that is over there. Let's say this is a radioactive material. So this is radioactive material. So now, of course, radiations will be coming from this and entering into the GM tube, and GM tube will take some reading. So it will take a reading of, let's say, 530 counts per minute. So out of these 530, obviously 20 was the background counts. So the count rate due to the substance only is 510 counts per minute. So that is the significance of background radiation that we always have to subtract it from the activity rate shown by the GM tube and placed in front of a radioactive material. Okay, now let's move. Let's straightforward jump to the questions now. Try to do some questions. Okay, let's read it. A reading is taken every 10 minutes of number of emissions per second from a radioactive source. The table shows the reading. So this is time and this is number of emissions per second. So at 0, 800. At 10, after 10 minutes, 560. After 20 minutes, 400. 30, 280, 40, 200, 50, 140, and 60, 100. So what is the half-life of the source? Okay, so let's say we start from here. So this is number of emission per second. So this is original activity rate, which is at the start. Original activity. That is always at time 0. Now you have to look for its half. So look for its half. So its half is 400. So it means that it took 20 minutes to get from 800 to 400. Like in order for 400 nuclei to become stable, 20 minutes are consumed. Again, if you look on the second half-life, half of 400 is 200, and then the time that it took is another 20 minutes. It means the half-life for this is 20 minutes, and that is option B. If we go to the next question for the decay curve graph, the graph shows how the decay rate of the radioactive source changes with time. Y-axis is decay rate, that is in decay per second. Decay means that when an atom is emitting its energy, then it is losing its energy is decreasing. So we say that nuclei is in decay process. So time is in days along x-axis. So the values are like 2, 4, 6, 8, and 10. And this is 1,000, 2,000, 3,000, 4,000, and the curve is till 4 days. So what will be the activity at 8 days? So they're saying that after 8 days, what would be the value of the activity? So we say that time and activity. So at 0, it is 4,000. And then at 2, it is 2,000. So it means its half-life is 2 days. Because in 2 days, the activity decay rate decreases to half. Okay. Then again, at 4, the activity decreases to 1,000. Okay, just keep going. After 6, it will be 500, and after 8, it will be 250. So it will be 250 decays per second after 8 days. Okay, next question. A sample of radioactive isotope has an initial rate of emission of 128 counts per minute and a half-life of 4 days. So what is this initial count rate? So this is like activity rate A0, which is 128. And then its half-life is 4 days. Now they're saying that how long it will take for the rate of emission to fall to 32 per minute. Okay, so we write time and activity over here. So we say that at the start, it was 128. The original is always at time 0. Okay. Then as its half-life is 4 days, so after 4 days, this will decrease to half of its value. 128 divided by 2, it will be 64. Then after another 4 days, means total 8 days, its activity again decreases to half, which is 32. So now, as the question was that 32 counts per minute, and this is 32. So this happens after 8 days. So the answer is C. Okay, let's go to the next question. A powder contains 400 milligram of radioactive isotope that emits alpha particles. Okay, this is the initial amount at the start, right? So we can write it like M0. Okay, the half-life of the isotope is 5 days. This is the half-life. What mass of this isotope remains after 10 days? Again, a very easy thing. So this is time and this is mass. So at 0, it is 400 milligram. So as half-life is 5 days, so after 5 days, it should be 200. And after another half-life of 5 days, that will make a total days of 10, this will be 100. So 100 milligram is the answer. Okay, next question. A redactor source produces a count rate of a detector of 1600 counts per second. So it means the initial value is A naught, which is the initial value. After 32 hours, the count rate has fallen to 100. So it means this is the final activity and this is the time in which activity drops from 1600 to 100. Both count have been corrected for background radiation. What is the half-life of the source? Again, the same thing. So 1600 is the start. So keep halving it. 800 and you have halved it for the one time. And then 400, you have halved it for the 2 times. And then again half it for the 3rd time. Again half it for the 4th time. It means that in order for the count rate to fall from 1600 to 100, 4 half-lives have been consumed. So we will say that as 4 half-lives are consumed, which is equal to 32 hours, because it took 32 hours for the activity to drop from 1600 to 100. So now divide both sides with 4. So half-life will be 8 hours. So 8 hours will be the answer. Okay, so I hope that you have understood the concept. In case of any ambiguity, you can contact me. Thank you so much, students. Take care. Bye.